Welcome back, class, and we will use this recording session to do some problems on the uh, diode models, right? The forward characteristic models that we talked about in the previous discussion, and I will also try and do a problem, if we have time, on the Zener diode and how you can use Zener diode in the breakdown region to in a voltage regulation application. Okay. All right. So I'm on slide 15, where we began studying these various models. I will skip ahead to where I have the first example or a problem. Okay. So on slide 17, we have a problem 436 from the back of the chapter. So let me quickly read what the problem is all about. A diode operates in a series circuit with a given R and VDD. So that's a simple basic diode circuit. A designer, an engineer, is considered using a constant voltage model but doesn't know whether he wants to use 0.7 volts or 0.6 volts for the VD. He can use either, but he wants to know what will be the difference in the calculated value of the current. Okay, let's see what he wants in A. For what value of VDD is the difference in the calculated value of current only 1%? Okay. So if he doesn't want to have an error or a difference between using 0.6 or 0.7, what should be the value of the bias voltage VDD so that the difference is restricted to 1%? So that's part A. Part B, for a given value of VDD, which is 3 volts and R of 1K, what two currents would result from the use of the two values of VD? So if you use 0.6 with those other values, what would be the current? If you use 0.7, what would be the current, and what's the percentage difference? So it's not too difficult a problem. Let's look to see how it is solved. So 4.36 is on page 5 of my PDF, so I'm on top of that page. So we are using the constant voltage model because that's what the engineer is trying to do in the problem. Okay, so we know the constant voltage model, you have to do the ID equals VDD minus VD by R. So he's struggling with two values, 0.6 or 0.7. So substituting those two values, we can set up two different equations for the current, ID1 and ID2. So in the first part, we are trying to solve the first part. We don't know the values of R or VDD, right? We have to find, in spite of not knowing R, we are supposed to come up with a value for IDD. So let's see how we do it. So ID2 should be not more than 1% higher than ID1, right? So ID2 equals 1.01 times ID1. So if ID2 corresponds to 0.6, then VDD minus 0.6 by R, right, that is ID2, is 1.01 times ID1, where we use the 0.7 volts in the equation. Now if you simplify this, you come up with VDD of 10.7 volts. So if he picks 10.7 volts, then regardless of which one he picks for the VD voltage, either 0.6 in the model or 0.7, his error in the current is not more than 1%. So that was part A. Part B, now he's given us some values, right? He's got a 3 volt source and he's got a R of 1K. So he says, tell me what the difference in currents will be if I went with either 0.7 or 0.6 as the VDD. So if you plug in those, you will notice that the two currents come out to be 2.3 and 2.4. So the difference is slightly higher, 4%. Okay. Okay, so that was that problem 436 from the textbook. I will move on to slide 23, and on slide 23 I'm actually looking at an example from the textbook. So this is example 4.5, and this should be in your textbooks. I think all of you probably have a copy now of the textbook I'm following. My actual textbook, believe it or not, is stuck in Chongqing. I had it, it got shipped to Chongqing. I don't have one now. So I'm also using the same PDF version that you guys have. That's why I'm copying and pasting to create my lessons. But anyway, let's see. I hope you can follow along on example 4.5. And let me walk you through quickly. It's a simple problem, so we don't even have to look at it. Let me just see, let me read out what we have. So in the circuit, in figure A, there is a simple R and voltage source and a D, a diode. So the voltage supply has a DC of 10 volts, but it has a ripple of a 60 hertz sinusoid of 1 volt peak amplitude. So the voltage, DC voltage, is coming from some kind of power supply, but unfortunately that power supply is also bringing a ripple or an unnecessary alternating current on the voltage. So this is an example of where we use the small signal model to solve for the problem. So given that there is a DC voltage of 10 volts and then there is a superimposed 1 volt peak sinusoid 60 hertz, he says find the DC voltage of the diode and the amplitude of the sine wave signal appearing across it. So we want to find the voltage across the diode, and also does any of the ripple also come across it? The ripple has a peak of 1 volt, right? DC peak voltage, but can you see that also on the diode? So that's the question. Okay, last thing he is telling us is that the diode is a 1 milliamp diode, which means at 1 milliamp current it drops 0.7 volts across it. Okay, so there's 3 quick steps to solving it. You can also see part B, the graphic, the circuit diagram on the top right. The current has been introduced, ID, it's flowing down, and part C is where we use our regular model, the small signal model. So looking at the solution on the bottom portion of the screen of the slide, starting from the left, first thing you do is to use that to find the current, the bias current, right? Given that the bias voltage is 10 volts and there is a resistor in 10K, and we know that the diode drops 0.7 volts, the current corresponding to that is 0.93 milliamps, which is close to the 1 milliamp. So it is in the good linear portion of the exponential response. Okay. So moving to the next step to the right, we have to find the RD, right? Remember that dynamic resistance or incremental resistance that I introduced when we did the theory. So that RD is nothing but the Vt, which is a constant value 25 millivolts, as you know, divided by the ID, which is 0.93 milliamps, and the ID we just calculated that. That gives us a value for the RD. That RD is what you use in the equivalent circuit in item C on the graphic, on the circuit diagrams on the right. So we now know the voltage drop across the diode, because we've been told that at 1 milliamp the voltage drop is about 0.7. We came up with a current close to 1 milliamp. So we are saying, okay, that means the voltage drop is roughly 0.7. So that's part of the answer. But the other part of the answer is there's a ripple, right? So what portion of that 1 volt peak comes out across the diode? So to solve that, we use the voltage divider formula, which you see to the bottom right. So the VD, the small VD, that means the AC value is, you take the V, the peak voltage of the sinusoid, and then you multiply that by the voltage divider ratio, RD by R plus RD, and you come up with the AC signal corresponding to the 1 volt peak, 1 volt peak 60 hertz ripple. So the voltage across the diode is a much reduced value. It's only 2.68 millivolts. So it's a less than 3% of the original 1 volt is appearing across the diode. But because it's so small, you can use that technique of just adding, right? Otherwise, you couldn't have. But we haven't come to that adding portion because he's not asking us for that. The next problem will use that adding technique. But here I just wanted to show you, and this is in the textbook so you can read it, how you calculate how to use the voltage divider method to find that portion of that original small signal transferred onto the output because of the presence of the diode. Okay, all right. So that was an example from the textbook. I will move to my lecture again, and that was slide 23. I have another example also on small signal on slide 24. This time we'll do some adding up. We actually use the small signal model. So this is, I call it problem small signal. It's not from our textbook, it's from outside. And let's see what it's being asked. So we are given a nice looking circuit with both the DC biasing voltage VDD shown separately and the additional small signal disturbance also shown separately. And the small signal disturbance again is a sinusoidal waveform. It has a peak voltage of 1 millivolt this time. In the previous example they gave us 1 volt, but in this case it's 1 millivolt and it's cos omega t. So similar, but the biasing voltage is only 1 volt, and the diode voltage is a little bit unusual. It's 0.4 volts. You don't see such diodes too often. Generally they are like 0.6, 0.7, but there do exist such small voltage diodes also. So this is a 0.4 volt diode. So given that, he's asking us, and also the circuit is drawn somewhat differently. The output is taken out from across the 1K resistor, not from across the diode itself. In the previous example, the voltage output was taken from the diode. In this case, it's taken from the resistor. But it's a small circuit, so we can always shift between the two voltages. So the question is asking us to find the V small diode or small d and V small out. So what that means is you have to sum up the individual outputs, one for the bias voltage and one for the small signal voltage, and then give the final result as the sum of the two using the small signal model. Okay, all right. So how to solve this? I'm sure by now you feel comfortable, you can do it, but let me go to this problem. It's on the top of page 6 of my PDF, and it's called problem small signal. So given VD equals 0.4 volts, which is the diode DC bias voltage, the small signal Vs is given as 1 millivolt, and the biasing voltage VDD is 1 volt. So find V diode and V out. First find ID, the diode bias current. Exactly what we did previously. In this case it came out to be 0.6 milliamps. So it's fine, it's still in the linear region. So Vd has been given to us to be 0.4. So if that Vd is what drops across the diode, then assuming that the signal is still not there, we are playing like superposition, we are ignoring it for the moment, then just because of the biasing voltage, the output voltage V out will be the biasing voltage minus the voltage across the diode. So that's the V out equals 1 minus 0.4 and you get 0.6. Now one other thing that we have to find immediately, because we already calculated the I diode, is to find the R diode, RD, right, the dynamic resistance. So that RD is nothing but Vt, the V thermal, divided by ID, and in this case that comes out to be 41.67. So next we deal with the small signal, right? So far we've only looked at the bias voltage, which is the big voltage. Now looking at the small signal, we can use that same voltage divider formula we just learnt about, and so V diode small equals, applying that RD by RD plus R to the Vs, the small signal sinusoidal voltage, you come up with a value of 0.04 millivolts as the portion of the 1 volt that appears on the output of the diode. So only a fraction comes across the diode. So what that means is much of the diode, the sinusoidal voltage actually gets transferred to the output in this case, right, because of the way it's connected. So almost that whole 1 volt is coming out as 0.96 volts. But across the diode, it drops significantly. It's a small fraction. So last step, to find those two voltages, the V diode and the V output, you add up both in each case. That means we add the bias voltage and the small signal voltage across the diode, and we add up the output by the bias voltage, whatever you call it, the remainder out after the bias voltage, and the small signal, and you write that in that form. Okay. So this is how you solve when you have a small signal situation. Okay. And it's an important thing to have learned, because we use a lot of this later on. Unfortunately, there's not too many problems in the textbook at this point. He kind of introduces us to this small signal idea, but doesn't give us too much to work with, and I couldn't find too many other problems. Once we go to transistors, we'll have many more small signal problems. But anyway, I hope you learned how the technique works. We went from having exponential curves to just simple addition. Okay. So I have two more problems to quickly solve. Actually, they are both examples, so I'm leaving it to you to go through them. I will just touch upon them briefly, and you can spend a lot of time looking through the details, leisurely. Okay. So I'm on slide 25, and we are looking at this example that pertains to voltage regulator. Now there's two kinds of voltage regulators in this chapter. One is when the diodes are in the forward biased condition, and the other is when they are in the reversed bias, but not just reverse, but severely reversed, but means breakdown region, Zener diodes. But this example 6.6, is still with forward biased voltages, diodes. So even forward bias voltages can be used for it. Now what is regulation? I've talked a lot about regulator, but here's a definition for what is a voltage regulator. That's first thing first. So voltage regulator is used to provide an almost constant DC voltage between its output terminals. So even if things vary, and what are the variations? So possible reasons for this change of voltage. That means the load currents are changing, right? The load resistances are changing, conditions are changing, so load currents are changing. So once currents are changing, the output voltage can be affected. So that's one way that the output voltage is not being constant. Secondly, there are changes in the DC power supply voltage, right? We assume that a power supply voltage is always, when we say plus 5 volts, it's like solid 5. But sometimes it's not a solid 5. It could drop a little bit to 4.9, 4.8, or go up, go down. So when all those are happening from the DC power supply, you still want a circuit that can prevent all those voltages changes to come to the output, right? So that's the purpose of having a voltage regulator to help us. So how can we use diodes to do this? And that's what the example teaches us. So please read the example. Let me read the question one more time. In a circuit, a string of 3 diodes is used to provide a constant voltage of about 2.1. So you can recognize that assuming each diode is at 0.7 volts, the normal operating voltage, so 0.7 times 3 in series gives you 2.1. So in theory, you can always get a nice 2.1 always out of the diode, out of 3. If you have 5, you get 3.5 and so on. So we want to with 3 you get 2.1. So what he is asking us is to calculate the percentage change in this 2.1 volts if, number one, there is a 10% change in the power supply voltage. If you didn't have these diodes, the 10% change in the power supply voltage would go straight to RL, right? Or straight to the output. Part B, if you actually connect a resistance, we know that as soon as you connect a resistance, even that can screw up the DC voltage. It can cause amps to increase or decrease, and thus voltage can change. So for both these conditions, we are asked to say how much will that 2.1 volt stay the same or change. Okay. Now I've written the solution here already. Corresponding to the plus 1 volt change, right? If there is a 10% change, that means plus 1 volt. The output only changes by 0.5%. So it's staying pretty good, right? Under open circuit conditions. B, that means open circuit meaning no load conditions. B, now you have a RL. As soon as you connect the RL, then what is the drop in voltage from that 2.1 volt, and it drops by about 20 millivolts. So those are the two answers, and I know again time is an issue, but let me quickly open up that question. It's on page 188, example 4.6, and you can see how we came up with the exact calculation. Okay. First, he calculates the RD for each one of them. It's about 3.2. So you really have a string of 3 resistances, right? So you can think of these 3 diodes as being replaced by 3 resistances. Once you have that, then the change in voltage across just the 3 resistances is easy to calculate, which is what he does using the voltage divider formula, and he comes up with that 19 millivolts peak to peak. 19 millivolts is peak to peak, so half peak is 9.5 millivolts. Okay. Then he does the load, connecting the load resistance, and he shows how to do that, and that comes out to be a change of minus 20 volts. Okay. Actually, this is including the change in the worst case change of 10% in the load voltage, the supply voltage. So with the supply voltage changing and the load resistance, you still only have a drop of minus 20 millivolts, which is pretty nice. Okay, so let me go and look at the last problem here that we want to look at, the Zener voltage example, Zener diode. This is example 4.7 in your textbook, and I hope again that you can spend some time looking through it and learning a lot. I will just hit on some of the important points. So we are given a 6.8 volt Zener diode, which is normally how they give it, and it also has some other data that's given by the manufacturer. It has that VZK, which is the V Zener knee voltage, as it's called, is sorry, that should be an I should change that, IZK, as 0.2 milliamps. Is also given the IZ is 5 milliamps and RZ is 20 ohms. So all these are here on this picture, but this data has been given to us. So first thing we have to do is to build the circuit model, right, using that data. And then once you plug that in, then here you see the circuit diagram showing the Zener diode. Remember, the Zener diode is always connected reversely. The cathode is connected to the positive of the voltage, and so this is the circuit, and there's a load resistance and there's a series resistance. We have to convert from here to here, so from part A to B, or graphic A to graphic B. And what is the difference? We have a RZ, just like for a regular diode, and then we have this V that also comes in, which is the Zener voltage, V0. So to go from here to here, we have to follow the steps. But what is the question being asked? This is a shunt regulator. Something connected in parallel is called a shunt. I think you already know that. And it's a regulator. So what is the diode circuit being asked to do? The supply voltage is nominally 10 volts but can vary by plus or minus 1 volt. So there's a 10% variation possible in the supply voltage. So given the 10%, how can we minimize the voltage, that 10% variation going to the load, is the question. So first part, so there's like F parts, A, B, C, D, E, F. It's a long problem. So first he asks us to find V0 with no load and V, the supply voltage, at its nominal value, 10 volts. Then, assuming that the full plus or minus 1 volt happens, tell us what changes to the output voltage happens. And that percentage change is actually called line regulation. It's a new term for you to remember. Then part C, he says, find the change in V out resulting from loading, right? Now you connect a load resistance RL, and so the way he's asking it, actually D and E are easy to follow. He just gives a value for RL and says, tell me what the change in. But in part C, he says, I'm connecting a load resistance that draws a current of 1 milliamp. So basically he's saying if there is a 1 milliamp change in the current, then how will the voltage change? How will the Zener diode prevent that voltage change from being too big, right? And then what happens is all these changes may push the voltage, the operating voltage of the diode. Remember, the voltage, the operating voltage of the diode has to be this 6.8 or minus 6.8. If you're not there or around that neighborhood, then you're not in the Zener region anymore, and you may never have any benefit of the voltage regulation. So that part also he tackles. So again, I will briefly open up but we are running out of time, so I'll just briefly open up the page where the solution is. It's example 4.7 on page 192. I request you to go through it, and you will see that the Zener diode does a great job of regulating the voltage to be much less. We have a 1%, 10% change in voltage, that means plus or minus 1 volt, but you will see that the changes in the output voltage are as low as like 20 millivolts and so on. Okay, and in the last step he finds that we are not in the Zener region anymore. Okay, so follow this. If you have any questions, let me know. Okay, I'm going to stop now.